Okay, so let's discuss the problem 8 of ISI Entrance Exam that happened yesterday. So the problem says we are given n positive integers a1, a2 and so on up to an, and their order is also given. A1 is less than or equal to a2 and so on is less than or equal to n is greater than or equal to 2, and another condition is given and the sum of the positive integers is equal to the product of the positive integers. And we are required to show is that the summation of I equal to 1 to n is less than or equal to 2n. And we also want to find when does equality occur. So let's look at the problem. So we are given the sum of the positive integers is equal to product of the positive integers. Now let's look at the case when n is equal to 2. We will solve this for n equal to 2 and we will build our solution for larger values of n. So for n equal to 2, the condition is that a1 plus a2 equal to a1 a2, and we want to show summation ai, which is a1 plus a2 is less than equal to 2 times 2, which is 4. This is what we want to show. So for n equal to 2, what we can do is we can directly solve this equation. We have solved different equations, so we can write it like this. We can add 1 to both sides. That will give us a1 a2 minus a1 minus a2 plus 1 equal to 1, and that will give us a1 minus 1 times a2 minus 1 is equal to 1. So we have a1 minus 1 times a2 minus 1 is equal to 1. And we know a1 and a2 are positive integers, so both of these terms are greater than or equal to 0. So the only way this can happen is both of them are equal to 1. And that will imply a1 is equal to 2, a2 is equal to 2. And what is a1 plus a2? A1 plus a2 is 4, which is less than or equal to 4. So what we can see is that when there are only two positive integers and the sum is equal to the product, that can only happen when a1 and a2 is both are equal to 2. And for two positive integers, the inequality a1 plus a2 less than or equal to 4 holds, and equality occurs for a1 equal to a2 equal to 2. So let's write this properly. N equal to 2, a1 plus a2 is less than or equal to 4 is true, and equality when, so for n equal to 2, for the sum to be equal to the product, the only case possible is a1 and a2 both are equal to 2, and in that case equality occurs. So for n equal to 2, we solved the problem. Now let's look at the other values of n. Now we are given the sum is equal to the product. Looking at this, what are the thoughts that come to mind? Firstly, the product is generally, the product of positive integers are generally very much larger than the sum of the positive integers, intuitively speaking. So products are generally larger than the sum. We know, we can intuitively feel it, right? So we have these products and they're equal, means this will not happen most of the time. Most of the time the product will be greater than the sum. So this will happen only for some specific choices of a1, a2 up to n. This will happen only for some specific choice of the n positive integers. Intuitively, you can feel that the numbers will not be very large. If the numbers are large, then the product will be larger, or product will be very much larger than the sum. You can see that the sum will not, if you increase the numbers, then the sum will not grow much than the product, and the product will grow very much. So the product will never be equal to the sum. So you can feel why the inequality, why there is an upper bound on the sum of the positive integers n. Some of the n positive integers. Because the numbers cannot be very large. If the numbers are very large, the product will be larger than the sum. This is the main intuitive idea. Now, Let's try to think. Now, just to have some intuitive motivation for n equal to 2, let's explore when does this occur? When does a plus b become less than the product? When does the sum of two integers become less than the product of the two positive integers? Let's try to explore this to get some intuitive idea. This will imply ab minus a minus b is greater than 0. That will imply ab minus a minus b plus 1 is greater than 1. We can add 1 to both sides. Again, in the same manner, we can factorize this. So we'll have a minus 1 times b minus 1 is greater than 1. And we know both are positive integers. So both of the terms are greater than or equal to 0. So for this inequality to hold true, what else should be true? Firstly, both of them should be strictly positive. Because if any one of them is 0, the product will be 0. It should be less than 1. Firstly, both of them should be strictly positive. Strictly positive means greater than or equal to 1. And both of them should not be equal to 1. If both of them are equal to 1, then the LHS will be equal to RHS. So when does this inequality hold? This implies a minus 1 and b minus 1 both are greater than or equal to 1 at least one of a minus 1 and b minus 1 is greater than 1. So a and b are greater than or equal to 2. So we can see when does the sum become greater than the product. Sorry, I mean the product becomes greater than the sum. The product becomes greater than the sum when a and b both are greater than or equal to 2. At least one of a comma b are is greater than 2. Then the product will become greater than the sum. So let's just try to figure out when does this hold? When which are the cases when the sum is greater than or equal to the product? This can happen only when, let's just assume a is less than or equal to b. This can happen only when a comma b is 1 comma 1 or a comma b is 1 comma 2 or a comma b is 1 comma anything. For a comma b 1 comma n, we will have that a minus 1 times b minus 1 is greater than or equal to 1. Wait. A minus 1 times b minus 1 is greater than 1. If any one of them is equal to 1, then the product is then the product is greater than the sum 1 comma n and 2 comma 2. For any other cases, both of the terms will be greater than or equal to 2 and at least one of them will be greater than 3. So we can see these are the only cases when the product can be less than or equal to the sum, and we are interested in such cases only. So we can see this does not happen all the time. We can see these numbers are small. These numbers are mostly 1 and 2. These numbers are not much larger. So let's try to see. So suppose we have, let's take the general case when n is greater than or equal to 3. We have the sum of the n integers is equal to the product of the n integers. And in this case, we cannot solve the equation because n is greater than or equal to 3. We cannot make the Diophant equation the way we made it earlier. So instead, what we can do is in such kind of scenarios, a substitution is useful, which is substitute ai as 1 plus xi, where xi is greater than or equal to 0. Why this substitution is useful? Because this gives you a way to compare the sum and the product. Why? We can see the product 1 plus summation product of 1 plus xi. If you expand this, this will have the terms, the expansion will look something like 1 plus summation xi plus summation xi xj plus summation xi xj xk and so on. I'm speaking intuitively. So you can see that the product has when you expand the product, you get these terms. When you get the sum also, you get the summation of xi's. So basically, why this substitution is useful? This gives you a way to compare the product and the sum. Compare how much large is the product compared to the sum. So let's substitute this. If we substitute, we say ai as 1 plus xi is greater than or equal to 0, we'll have summation ai equal to product of ai. So we give summation 1 plus xi. This will give n plus summation xi equal to product of 1 plus xi. Now, xi is greater than or equal to 0. So what? So now look at one thing. Here we explore when does the sum become greater than or equal to the product. You can see when the numbers are mostly equal to 1. This is the intuitive thought that when the numbers are mostly equal to 1, then the sum becomes greater than or equal to the product. In the most of the other cases, the product is generally greater than the sum. So let's try to see. So I told that the sum can be equal to the product when most of the AIs are equal to 1. Most of the AIs are equal to 1. That will mean most of the XIs are equal to 0. Okay, this product will look like, if we expand this product, this will be 1 plus summation xi plus summation xi xj plus summation xi xj xk and so on. You can see most of the xi's is 0. That will mean most of the terms in this product will be equal to 0. I'm speaking intuitively. Most of the terms in this product will be equal to 0. So we are not interested in all the terms in this product. We are only interested in some of the terms. And also what we can say is that here we also know that x1 is less than equal to x2 is less than equal to so on, less than equal to xn. Now let's try to explore the edge cases. We know xn is greater than or equal to 0. But can xn be equal to 0? Let's try to figure out a lower bound for xn. Because intuitively, what does it feel? Intuitively, we saw that the second term is always greater than or equal to 1, greater than or equal to 2, generally, mostly. So, and here also xn is the largest term. So, we would like to find a lower bound for xn. So, can xn be equal to 0? Let's remove all the edge cases. Suppose xn equal to 0. In that case, we know all the xi's are greater than or equal to 0 and all the xi's are less than or equal to xn, which is equal to 0. That will mean all the xi's are equal to 0, which will mean ai's are equal to 1, and then summation ai will be equal to n, product of ai will be equal to 1. And as n greater than or equal to 3, you can see that these two can't be equal. So this implies xn can't be equal to 0, which means xn is greater than or equal to 1. Let's ask further. Can xn be equal to 1? Suppose xn equal to 1. What we know is xi's are all less than equal to xn. So xi's are less than equal to 1. And that will mean summation xi is less than equal to summation 1, which is equal to n. That will mean summation xi is less than equal to n. Right? And remember one thing, what do we want to show? We want to show summation ai is less than equal to 2n, which is true if and only if summation 1 plus xi is less than equal to 2n, which is true if and only if n plus summation xi is less than equal to 2n, which is true if and only if summation xi is less than equal to n. So we want our new problem is to show summation xi is less than equal to n. And here you can see in the case when xn is equal to 1, you already have shown that summation xi is less than equal to n, because all the xi's are less than equal to 1. In the case when x is equal to 1, so you already have summation xi equal, less than equal to n. Now, so inequality is true. What is the equality case? Equality when does equality occur? We had xi is less than equal to 1 and we summed all the inequalities. So equality can only occur when all the xi's are equal to 1. Equality can only occur when all the xi's are equal to 1. And that will mean all the ai's are equal to 1. In this case, we are talking about the case when xn is equal to 1. So all the xi's are equal to 1 for equality to occur. That will imply all the ai's are equal to 2. So what does that mean? That will mean summation ai is equal to 2 plus 2 plus 2 and so on. This will be equal to 2n because this is n times, and product of ai will be similarly 2 power n. Now, and you must have the sum equal to the product. 2n must be equal to 2 power n when n is greater than or equal to 3. Now you know one thing is that here for n equal to 3, look, the left hand side is a linear term and the right hand side is an exponential term. So you can see that they will not be equal. They will not be equal for most of the values of n, for larger values of n. So for n equal to 3, you can see 2n is 6 and 2 power n is 8. So 2 power n is greater than 2n for n equal to 3. And for larger values of n, 2 power n will grow exponentially and 2n will grow linearly. So you can tell that 2 power n will be greater than 12 for all n greater than or equal to 3. So let's just quickly prove this. 2 power n is greater than 12 for all n greater than or equal to 3. For n equal to 3, this is true. Let's say this is true for some n equal to k, where k greater than or equal to 3 means 2 power k is greater than 2k. We would like to show for n equal to k plus 1. So let's check 2 power k plus 1. 2 power k plus 1 will be 2 power k times 2. This will be greater than 2k times 2 because 2 power k is greater than 2k. This is equal to 2k plus 2k, and as k is greater than or equal to 3, you can say that 2k is greater than or equal to 6. Means 2k, you can write 2k is greater than 2. This 2k is greater than 2. This, so 2k plus 2 is equal to 2 times k plus 1. So you can see if you compare these two things, you have that 2 power k plus 1 is greater than 2 times k plus 1. So by induction, you can say that 2 power n is greater than 12. So what is the conclusion? Conclusion is that when xn equal to 1, inequality summation xi less than equal to n is true and equality can't occur. So this is what we figured out up to now. Let's look at the other cases. We have analyzed the case when xn equal to 0 and xn equal to 1. Now let's look at the case when xn is greater than or equal to 2. When xn greater than or equal to 2, let's look at one thing. Let's see one thing. We have this product of 1 plus xi. This will be something like 1 plus summation xi plus product of xi xj plus product of summation of xi xj xk and so on. We already showed that the most of the terms in the product will be 0 because we saw for the sum to be equal to the product, most of the ai's will be equal to 1, which will mean most of the xi's will be equal to 0. Most of the xi's will be equal to 0. That will mean most of these terms will go to 0. So I am not interested in all the terms. I am interested in only some specific non-zero terms. So and look at the terms after this. When you have product of more than or equal to 3 terms, you can tell that most of the terms will be equal to 0 because you have x1 is less than or equal to x2 and so on less than or equal to xn. One thing that you can guarantee is xn is non-zero, except that most of the terms are equal to 0. Most of the terms are equal to 0. So you can say that we will not be interested in all the terms. The terms which have more than or equal to three terms is involved, we will ignore those terms for now. So let's see, we have product of 1 plus xi. This is equal to 1 plus summation xi plus summation xi xj plus summation xi xj xk and so on. This is, we can say this is greater than or equal to 1 plus summation xi plus summation xi xj. We can write this because all these terms are greater than or equal to 0. So we can write this inequality. Now, and these terms, let's look at the summation xi xj. What is the summation xi xj? Summation xi xj is xn times x1 plus xn times x2, so on. Xn times xn minus 1, xn minus 1 times x1, so on. Xn times xn minus 2 plus. So you can say in the summation xi xj, these terms will be involved. And in the summation xi xj also, I will not be interested in all the terms. Let's look at the terms only involving xn. Because what we know is xn is non-zero surely. So let's look at the terms which involve xn. So we can write another inequality. This summation xi xj will be greater than or equal to. You can set the limits for I comma j. Okay. The only thing that matters is we know summation xi xj. This will be greater than or equal to this product xn x1, xn x2, and so on xn times xn minus 1. Let's ignore all the other terms. We can all the other terms will be greater in the summation xi xj will be greater than or equal to 0. So we can say summation xi xj will be greater than or equal to this. Let's substitute this in this inequality. So what we will get, we will have product of 1 plus xi equal to 1 plus summation of xi plus summation xi xj greater than or equal to, this is greater than or equal to 1 plus summation xi plus xn times x1 plus x2, so on up to xn minus 1. Okay, now, and we know product of 1 plus xi is equal to n plus summation xi. And remember, we want to, and so this summation xi cancels out. We have n is greater than or equal to 1 plus xn times x1 plus x2, so on up to xn minus 1. So we want to, and remember what we want to show. We want to show summation xi is equal to, we want to show summation xi is less than or equal to n. Let's write everything again. We need to, what we have is that n is greater than or equal to xn times 1, x1 plus so on up to xn minus 1. For now, let's call x1 plus so on up to xn minus 1 equal to a and xn equal to b. We want to show summation xi. Summation xi is what? A plus b. We want to show a plus b is less than or equal to n. And we have n is greater than or equal to 1 plus ab. This is what we have, and this is what we want to show. A plus b is less than or equal to n. Now, what do you know? What is the relation between these two terms, 1 plus ab and a plus b? If we can so what is our intuitive thought? If we can somehow show that 1 plus ab is greater than or equal to a plus b, then the inequality will follow. Then it will follow that a plus b is less than or equal to n, and our proof will be done. And 1 plus b is greater than or equal to ab. When does this hold? We have already explored this case. So when does 1 plus ab greater than or equal to a plus b? When does this hold true? This will hold true when ab minus a minus b plus 1 is greater than or equal to 0. This will hold true when a minus 1 times b minus 1 is greater than or equal to 0. And as a and b are positive integers, so this will hold true when both of them are greater than or equal to 0. Now let's look at one thing. We know xn is xn is greater than or equal to 2, which is greater than 1. So you know xn minus 1 is greater than 0. So you know xn minus 1, which is basically xn is equal to b, which is basically b minus 1. Xn minus 1 is greater than 0. So you know b minus 1 is greater than 0. What is we would like to show a is greater than or equal to 1. That is, we want to show x1 plus x2 and so on up to xn minus 1. We want to show this sum is greater than or equal to 1. You can see this will be mostly true, but let's just figure out why this should be true. Claim x1 plus x2 and so on up to xn minus 1 is greater than or equal to 1. Suppose not, what does that mean? That will mean x1 plus x2 and so on up to xn minus 1 should be equal to 0, and that will mean all the xi's, that is x1 equal to x2 equal to so on up to xn minus 1, all of them are equal to 0, and xn is greater than or equal to 2. Now, can this happen? Let's check. We have summation ai is equal to n plus summation xi, which is equal to n plus 0 plus so on plus 0 plus xn, which is equal to n plus xn. And what is product of ai? Product of ai is basically, you know, this is 1 plus x1 times 1 plus x2 and so on, 1 plus xn minus 1 times 1 plus xn. This is equal to, you know, x1 is 0, x2 is 0, xn minus 1 is 0. All of them are equal to 1. So the product becomes equal to 1 plus xn. So you must have the sum equal to the product. Sum is n plus xn, product is 1 plus xn. Sum is n plus xn and product is 1 plus xn. But you know this cannot hold true because n is greater than or equal to 3. So this implies our claim is true, which means x1 plus x2 plus so on up to xn minus 1 is greater than or equal to 1. And we know that this was equal to a, so we know a is greater than or equal to 1. And b, which is equal to xn, we know this is greater than or equal to 2, b is greater than 1. What does that mean? That means a minus 1 times b minus 1, you can, as both of the terms are positive, so you can write a minus 1 times b minus 1 is greater than or equal to 0. That will mean ab plus 1 is greater than or equal to a plus b if we expand the product. And we already have shown that n is greater than or equal to 1 plus ab. This is, we already have n is greater than or equal to 1 plus ab. This is, you have n is greater than or equal to ab plus 1 is greater than or equal to a plus b. So you have n is greater than or equal to a plus b, which is equal to summation xi. This is what we wanted to show. Now we need to find when does equality occur. Remember, suppose equality occurs, what does this imply? This means equality must occur at this place also. We showed that n is greater than or equal to ab plus 1 is greater than or equal to a plus b. For this equality to occur, we must have this equality also. We must have ab plus 1 equal to a plus b. This equality should also be true. This will imply a minus 1 times b minus 1 is equal to 0. But we know b minus 1 is greater than 0 because b was greater than or equal to 2. This implies a is equal to 1. This implies x1 plus x2 and so on up to xn minus 1 is equal to 1. Now when can this happen? Remember, these are all positive integers. Now that, and we know xn minus 1 is the largest among them. This can only happen when x1 equal to x2 and so on up to xn minus 2 equal to 0 and xn minus 1 equal to 1. Because xn minus 1 is the largest, only one of them will be equal to 1 and all of them will be equal to 0. So equality to happen, we must have this to be true. And we must also have the sum of ai equal to product of ai. Okay, so we have x1 equal to x2 equal to so on up to xn minus 2 equal to 0, xn minus 1 equal to 1. This means a1 equal to a2 equal to so on up to an minus 2 equal to 1 and xn minus and an minus 1 equal to 2. Let's try to find the sum. Sum will be 1 plus 1 so on 1 n minus 2 times plus an minus 1 which is 2 plus an equal to product will be 1 times 1 so on 1 be n minus 2 times 2 times an. So this you can write, this will be, this sum will be n minus 2, n minus 2 plus 2 plus an equal to, this product will be 2 times an. This implies n plus an equal to 2 times an. This implies an is equal to n. So what we have proved is that if equality holds, this must imply a1 equal to a2 equal to so on up to an minus 2 equal to 1, an minus 1 equal to 2 and an equal to n. Now let's check. Now let's check. Does equality occur in this case? We already know sum. The sum is equal to 1 plus 1 so on plus 2 plus n minus 2 times. This is equal to n minus 2 plus n equal to 2n. And product of AIs are equal to, you can say all of them are equal to 1 and an minus 1 is 2 and an is n. So the product of them is also 2n. So the sum is equal to the product, and let's check the equality if equality holds. And equality also holds because summation ai is equal to 2n. So we have checked that, we showed that if equality holds, then we must have that a1 equal to a2 equal to so on up to an minus 2 equal to 1, an minus 1 equal to 2 and an equal to n. And we also check that equality also holds for this. So what is our final answer? So for n equal to 2, inequality holds, we showed, and equality when a1 equal to a2 equal to 2, for n greater than or equal to 3, inequality holds, we prove, and equality when a1 equal to a2 equal to so on up to an minus 2 equal to 1, an minus 1 equal to 2 and an equal to n. So this is the answer.